Alright, so in this video we're going to focus on Newton's second law for rotation again, but we're going to combine it with Newton's second law, the translational version as well. So this is an example of where these two kind of areas come together. And so what we have here is a block, and the only thing that it's happening is that it's got this string attached to it which is wrapped around this disc. Now, based on the problems we've done in the past, the acceleration of this block would be 9.8 meters per second squared. It would be in free fall, because we'd say, well, this disk doesn't provide any resistance to its acceleration, so it would be in free fall basically, just like if there was nothing attached to it. But because this disk has mass and it's being accelerated, then we have to account for that acceleration. Okay, and so the way that we analyze this problem is by kind of putting together our knowledge of net torque and net force. Okay, so we'll start by writing a net torque equation for this disk right here. Okay, so what we're going to do is let's draw a diagram for the disk and for the block. So we have the disk, and we have a downward force on it of tension, and then we have the block here with a downward force of gravity and an upward force of tension. Okay, so we'll start with the disk. So this is going to have rotational acceleration. It won't have linear acceleration, but rotational acceleration. And so this disk at its center also has gravity pulling it downward and a normal force pushing up on it. But we can ignore these from the rotational sense because they're acting at the radius, which means they provide no torque, because no radius means no torque. So we're going to go ahead and ignore those because they don't affect the rotation here. Okay, so let's do a net torque equation for the disk. So the sum of the torques is going to add to be I alpha, and that will be equal to the force of tension times that downward radius. Okay, now we have to decide if we want that to be positive or negative. So generally, remember, counterclockwise is positive, so we could say this way is positive, or we could say that this way is positive. It doesn't matter. We can actually do it either way. For this one, let's just go ahead and say that this way is positive. Okay, so we're saying that this is causing a positive torque. Even though it's backwards, it'll make it easier from the sense of this part right here. And we'll end up with a positive acceleration. Okay, and so let's go ahead and substitute in the values we know. We know that R is 20 centimeters. Well, actually, let's leave this alone. So we're just going to solve this without plugging in numbers till the end. But we do know that since this is a disk, the moment of inertia of a disk is 1/2 times mr squared. So 1/2 mr squared times alpha is equal to t times r. Okay, so moment of inertia times the acceleration equal to the torque, which is tension times the radius here. Okay, so we'll do a second equation for this block, and so for this one, it's not rotating, it's linear, so we're going to say that the sum of the force is equal to ma, and we have this downward force, the weight, minus this upward force of tension. Okay, and so we can solve this for tension and substitute in this equation here. And so we could say, so T is equal to ma, sorry, it would actually be mg minus ma. So we'll add T to the other side and subtract ma over. And so we can plug this in to here, and so we get that the 1/2 mr squared, our moment of inertia, times our angular acceleration is equal to our tension, which is mg minus ma, times the radius. Okay, so it's asking for angular acceleration. Let's actually solve for the linear acceleration first. Okay, so what we're going to do here, the next step, is that we have too many variables. So we know what r is, we know what m is, we know what g is, but we don't know what a is, and we don't know what alpha is. Okay, but what we do know is that these are related. Okay, remember that angular quantities and linear quantities are related just by multiplying the radius. So if we can replace alpha with a over r, then we can go ahead and solve for the acceleration. Okay, so you divide r over and get that alpha angular acceleration equal to a over r. So we have 1/2 times m r squared times a over r is equal to mg minus ma times r. So I can divide that r over, and then what's going to happen is this r and this r are going to cancel with these two. So we can get rid of those. Also, since we have every term has mass in it, we can divide out the mass. So we end up with just that 1/2 times a is equal to g minus a. So if we add a over, we get that 1.5a is equal to g, or that a is equal to g over 1.5, which would be, this gives us 6.53 meters per second squared of acceleration. Then if we want to go here and solve for angular acceleration, we would just divide that by the radius of 0.2 meters and get an angular acceleration of 32.7 radians per second squared. Okay, and that's it. That's Newton's second law for rotation. Okay, so at this point, this video was pretty short. This is probably the hardest thing we're going to do. If you're confused, I know it was a lot of stuff, I encourage you go back over this same video. Okay, watch through it again, skip back and see a part that was giving you trouble, and then once you kind of come through it again, let me know if you have a question, okay, and we'll see if we can answer that question in class.